Section 5.2, Proving Trigonometric Identities. So in Section 5.1, we talked about simplifying using trigonometric identities, and now what we're going to do is we're going to prove that things that don't really look like identities really are two things that equal each other. So we have these things that we know. Okay, I pulled this off of just somewhere, so it doesn't look exactly like what we have, but use what you have on your circle card. It's basically the same thing. We have the reciprocal identities where, you know, if you flip sine, you get cosecant, and so on. Pythagorean identities, which are new to us as of 5.1, where you have like sine squared plus cosine squared equals 1. The quotient identities, tangent is sine over cosine, cofunction, and then I've never heard of this parity identities part of this, but even and odd, right? We know the even and odd functions and what happens with them. The book lists quite a few strategies, and I try to like condense them basically. One strategy that you're doing, and these strategies are also true for just simplifying trigonometric expressions like we did in 5.1. One thing you can do is, if all else fails, change everything to sine and cosine so that things will cancel out. The next strategy is work with the more complicated side, and then if like you get stuck, if you get something, you get the more complicated side simplified to something fairly simple, but it doesn't match up the other side, just try working with the other side. Factor and find a common denominator if you have two fractions. Those are some things that you can try if you don't know what else to do. So the actual like first problem in the book has you proving an algebraic identity, I guess, to get your feet wet before they throw in sines and cosines and all that jazz. And so I'm going to walk you through this. And I want to point out this equal sign means that these two expressions are equal, the expression on the left and the expression on the right. We're saying those are the same. But this does not mean that I can do normal equation things, okay? By proving the algebraic identity, I'm going to work with one side of my equation, this side. I'm going to work with it until I get that it equals 2, and then I'm done, okay? And that process I'm going through is my proof, and like I said, the reasons, like in geometry, I don't know if I actually said this. In geometry, when you did proofs, you had like steps and then you had reasons. Well, we're all going to know what the reasons are for what we're doing. For example, if I start this proof, because I have an x squared on top and an x on bottom, my first inclination is to factor the top because that's the difference of two squares. We could probably do this by getting common denominators. It would take a whole lot longer, if I'm not mistaken, but this is a really great way of doing this. Both of those are the same on top. They both are the difference of two squares, okay? And so this is what we end up with if we factor on top. Now that's great because look, I can cancel out x minus 1, x minus 1, and then x plus 1, x plus 1. The reasons for these, like the reason for writing the first step was factoring by the difference of two squares. Well, any math teacher is going to know that's what you just did. So that's why we're not having to write the reasons, because these are things that we all know are true, or hopefully will after this section. So what I'm left with here is x plus 1 minus an x minus 1. Make sure you remember to distribute the negative there. So this is x plus 1 minus x plus 1 equals 2. And x minus x is 0, 1 plus 1 is 2, and 2 equals 2, which means we're done. It's like a puzzle, really, if you want to look at it. They give us this thing on the left side. We have certain rules that we're allowed to follow. We can't like add or subtract something to both sides. We can't cross multiply. We can't do anything to both sides at once. We have to just work with one side at a time. And our goal is to get this left side to somehow end up being 2. And look, we accomplished our goal. So there's nothing really to circle here. It would not be appropriate for me to circle 2 equals 2. I mean, I can if I want to, but that's not my answer. My answer is the whole proof. So a lot of people like to make some kind of symbol here at the end to show that they're done. Like I like to make a smiley face when I'm done with proofs because I'm like, hey, I just finished a proof. That's pretty awesome. But you could do whatever. I would love to see lots of smiley faces personally. I'm sure Mr. Hazel would also love to see smiley faces all over your papers, so go for it. But that's without trig, a way of proving an identity. So now let's throw some trig in here. Prove the algebraic identity. Tangent x plus cotangent x equals secant x cosecant x. So this is not an identity that we know. It's not an identity that we need to memorize, but they're telling us the left side equals the right side if we do enough simplification. So I'm going to choose to work with the left side because I have a plus sign here. I know that I can write tangent as sine over cosine, which gives me a fraction. I know that I can write cotangent as cosine over sine, which gives me a fraction, and I'm adding those fractions together, which means I need common denominators. The common denominator here would be cosine x sine x, because it has both the denominators. This fraction is missing a sine x. This fraction is missing a cosine x. So on top here, I would have sine squared x plus cosine squared x. Okay, and all along the way here, we could keep writing what it equals. And it's a good idea every now and then to write what it equals so that you don't forget what your goal is. But you don't have to rewrite it every time unless your teacher tells you you have to, and then you know what, go for it. Okay, now from here to simplify this, sine squared x plus cosine squared x is an identity. Sine squared x plus cosine squared x equals 1. It's a Pythagorean identity. You need to get very used to recognizing that. That is true. Okay, so we have 1 over cosine x sine x equals secant x cosine x. I meant to put cosecant here. It's important to always write down the problem correctly. Otherwise, you can mess up really easily. Okay, now 1 over cosine, isn't that secant? 1 over cosine is secant, and 1 over sine, isn't that cosecant? So didn't we just get to our goal? Yes, we did. So smiley face. We're done. There's at least 1 or 2 problems where you have to do this where they basically, instead of giving you an identity, they give you some choices that could be what your identity here equals, and you have to figure out which one it is, and then it says confirm the match with a proof. Well, the easiest way to figure out which one of these is right is by doing the proof itself. Like, let's sit here and simplify 1 over secant minus 1 plus 1 over secant x plus 1. Let's simplify that and see which one we get. So I would get a common denominator here. So my common denominator is going to be secant x minus 1 times secant x plus 1, because I'm just going to combine these together, multiply them together, and get my common denominator. Sorry, that means that I would multiply this fraction by what it's missing, which is secant x plus 1, multiply this one by secant x minus 1, and then get the top of our fraction here. That's really nice that we're just multiplying it by 1 on both of those. So I should get this on top. And then secant x plus 1 plus secant x minus 1, well, there's going to be some things that simplify there. Secant x plus secant x is the same as saying x plus x. X plus x gives me 2x, so secant x plus secant x gives me 2 secant x. 1 minus 1 gives me 0, so I don't need a number there anymore. On the bottom here, we want to FOIL this out because it's going to give us secant squared x. Outer and inner cancels out, and then I get minus 1. We want to do that because that's going to give us an identity, secant squared x minus 1. If we use 1 plus tangent squared x equals secant squared x, if we use that Pythagorean identity, all we have to do is subtract the 1 over to this side, and look, we have what is on the bottom of our fraction. So the bottom of our fraction really equals tangent squared. So 2 secant x over tangent squared x. Okay. Now, hopefully at some point, you know, either soon or maybe we already realized there's a 2 that we're probably not going to be able to get rid of. So there's a really good chance that this is going to match up with I. So that kind of gives us a goal to work toward. Is that it's probably going to be I. Let's go ahead and change this these to sines and cosines now. So this would be 2 over cosine, because secant is 1 over cosine, but I have a 2 in front instead of just nothing. Tangent squared is sine squared x over cosine squared x. Now I would flip up that fraction and multiply by cosine squared x over sine squared x to keep simplifying here. So one of these cosine x's, or this cosine x goes away and cancels with one of those cosine x's. Okay, so now I have 2 cosine x over sine squared x. And we might be asking ourselves, did that really help us? And, kind of a matter of opinion. I'm going to come back up here and start writing. Here is something tricky that hopefully after this you'll be able to recognize. I can split 2 cosine x over sine squared x into 3 different fractions. 2 over 1 cosine x I can pair up with one of my sine x's. Then the other sine x doesn't have anything to pair with. And the reason this is helpful is because this is really 2 cotangent, because cosine over sine is cotangent. 1 over sine is cosecant. And I just got this one up here. Okay, so I just proved that that really is which one matches with this. Okay, and I circled my answer, but a smiley face would also be appropriate. Example 4. On example 4, we want to use the difference of squares property. Basically, we want to say this 1 minus sign, if I want to work with the left side here, the 1 minus sign on the bottom, I can do something with, because if I times it by its conjugate, remember that means that it's the same thing but with the sign changed in the middle. If I times top and the bottom by the conjugate of the bottom, then some nice things are going to happen. I'm going to leave the top undistributed for now. Okay, and then on the bottom, because these are opposite signs, this is going to end up being 1 minus sine squared t. And 1 minus sine squared t, I don't know if you realize this, but that's totally an identity. If we start off with our Pythagorean identity, cosine squared plus sine squared equals 1. If I subtract the sine squared over to this side, 1 minus sine squared equals cosine squared. So the bottom of this fraction is really cosine squared. So that's cosine t times 1 plus sine t is over cosine squared t. Oh, what do you know? I can cancel out this cosine t with one of the cosine t's on the bottom, which gives me 1 plus sine t over cosine t. And at this point you might be like, I have no idea where to go from here. And then you'd realize, hey, this is what I was going for. I wanted it to be 1 plus sine t over cosine t. Okay, so I'm done with that proof. Hooray! But basically, because we don't have any squareds here, we can't try to use a Pythagorean identity to start off with. They're all sines and cosines, so there's nothing we can do there. So basically, all we can really do is say, well, what if I multiply by 1 plus sine t on this side? Okay, or if we wanted to work with the right side, if we multiplied by 1 minus sine t, that would work. And we just go from there. Example 5. So this one's a tricky one because both of these sides seem kind of unpleasant and difficult to work with. So let's just see if there's anything that we can do with the left side. Now, I may have commented to some of you at some point that it's almost never a good idea to change like cotangent squared into its identity, which would be cosecant squared u minus 1. And the key thing there is it's almost never a good idea, but that means sometimes it is. And the way you know is if I have 1 plus cosecant u on the bottom here, if I change cotangent squared to cosecant u minus 1, then I can factor the top here into cosecant u plus 1 times cosecant u minus 1, and then I will be able to cancel out, because 1 plus cosecant u is the same thing as cosecant plus 1. Okay, so this and this cancel, and that gives me cosecant u minus 1. Like so. Okay, and that's about all I can think to do with that side personally. So let's start working with the right side. So we're allowed to do this as long as we work with one side at a time, and then now I can switch and say, okay, what can I do with the right side of this? So cotangent u, I can change to be cosine u over sine u. And then on the inside, what I really want to work with is I can make this 1 over cosine u minus sine u over cosine u. I already have common denominators, which is great. I love having common denominators. They're the best. So that makes this 1 minus sine u over cosine u. And so then hopefully we all see, hey, cosine u cancels. So that's 1 minus sine u over sine u. And this is the point where I feel like it's a little bit tricky to realize your next step, because we just aren't used to doing this. If I have 1 minus sine u over sine u, I can rewrite that as 1 over sine u minus sine u over sine u. Basically split up. This is really two fractions where this is over this and this one's over this, and split it up. The reason I would do that is because 1 over sine is cosecant and sine over sine is 1, and ta-da, I just got my sides to match up. So that's an example of a more complicated one where you might have to work with both sides of your equation. Okay, but notice I did it one at a time. I didn't try to like cross multiply, didn't add or subtract things from both sides. I just worked with one until I felt like I was in a good place, and then I switched to the other side and started working with it. So that's totally the same example, and we're not going to do it a second time, so that's my bad. That's the basic gist of what we're doing with proving identities. So the problem with these is that it might seem really hard to you. You might feel like, I just don't know what to do. I don't know where to start. And that's fine. These are really about as close to puzzles as you can get in math. And if you like puzzles, then great. You should hopefully really get a kick out of this once you understand how to do it. But the thing is you have to start somewhere. Like if you look at this one that we started off on, I mean, this is going to be at the end of the closer to the end of the section where they're expecting you to have picked up on some things. It's fine if you had no idea where to start this, okay? But by the time we're done with 5.1 through 5.4 and we're ready to take the test, then you should have practiced enough problems, gone through enough problems that you should be able to at least start this even if you couldn't finish it. Okay, this is a harder one, and I get that. But you have to remember, the general strategies that I stuck up at the beginning. If you don't know what else to do, change everything to sine and cosine. Work with the more complicated side. If there's a place you can factor, do it. If you can, find a common denominator. And then sometimes it's helpful to multiply by the conjugate to try to get a difference of squares. But, just keep plugging away, and obviously ask for help when you need it, and you will soon be trigonometric identity proving masters.